Okay, so geometry practice. We're going to go ahead and just work our way down the list I provided on D2L. First up is beryllium fluoride, BeF2. Now, beryllium gives us 2 valence electrons. Each of these fluorines gives us 7. There are 2 of them. So we have a total of 16 electrons to play with. So beryllium, fluorine, fluorine. Those 2 bonds use up 4 of our electrons. And we have 12 electrons left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that uses up all 12. Total of 0 electrons left. And that is it for beryllium fluoride. When you treat this as a covalently bonded compound, beryllium is an exception to the octet rule, similar to boron. It only needs the 4. It's just weird like that. Now, as for its geometry, beryllium fluoride, it has 2 electron domains, 0 non-bonding pairs, giving it a linear geometry. This is the polarity of each of its bonds. They cancel out. It's nicely symmetrical. It is non-polar. So that is the molecular geometry and polarity of beryllium fluoride. Next up, boron trichloride. Okay. Boron gives us 3 electrons. Chlorine gives us 7. And there are 3 of them. So we have 24 electrons to play with. Boron goes in the middle, bonded to each of the chlorines. That uses up 6 electrons, leaving us with 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And that uses up all of our electrons. And boron is the very common exception to the octet rule. It only needs 6. It can take 8, but it's happy to stop at 6, rest along the way. This gives us 3 electron domains, 0 non-bonding pairs. So it has a trigonal planar geometry, and it is, once again, nonpolar. Nicely symmetrical, no deviation there, no broken symmetry. Now phosphorus pentabromide. Alright, phosphorus gives us 5 electrons. Bromine gives us 7, and there are 5 of them, for a total of 40 electrons. Phosphorus, 1, 2, 3, 4, 5. Oops. That uses up 10 of our electrons. We have 30 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, oops, it's 18, 20, 22, 24, 26, 28, and 30. So phosphorus is in the 3rd row, so it has those unused d orbitals, so it can have more than 5 bonds, so that's not a problem. This gives us 5 electron domains, 0 non-bonding pairs. This means that it has a trigonal bipyramidal geometry, trigonal bipyramidal electron domain geometry, and a trigonal bipyramidal molecular geometry. And it is fully nonpolar, nicely symmetrical. The structure kind of like this. The two poles cancel each other out, and the triangle in the middle cancels each other out. And here we have carbon tetrachloride. 4 electrons from carbon, 7 from each of the 4 chlorines, giving us 32 electrons. Carbon, chlorine, 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 chlorine. That uses up 8, leaving us with 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Notice that the non-bonding pairs, the electrons just always come in pairs, whether they're in bonds or in non-bonding pairs. You only leave electrons unpaired if you absolutely have to, if you have an odd number of electrons. And that's something I saw the other day several times. Never leave electrons unpaired unless you have no choice. All right, so that uses up our 24 electrons. And now everyone is happy. Carbon has 8, each chlorine has 8. 4 electron domains, 0 non-bonding pairs. For a tetrahedral geometry, it is a fully symmetrical molecule. In 3 dimensions, the bonds are, each bond is polar, but they cancel each other out in a 3-dimensional math that is not the worst thing in the world, but it's not particularly pleasant. So it is nonpolar. No broken symmetry. Now we have sulfur hexaiodide. Sulfur gives us 6 electrons, 7 from each of the iodines. There are 6 of them. A total of 48 electrons. So sulfur, iodine, 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 iodine. Those 6 bonds use up 12 electrons. Sulfur is also in the 3rd row. It has d orbitals available. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. That uses up all of our electrons. Gives us 6 electron domains and 0 non-bonding pairs. Or an octahedral geometry. Once again, fully symmetrical, no broken symmetry, nonpolar. Each bond, though, is polar. Well, I shouldn't necessarily draw it like that. Sulfur and iodine make for a complex case. This is interesting. BH2, 1 minus. Boron gives us 3 electrons. Hydrogen gives us 1 each. Then we subtract our -1 charge. Never forget the charge. Be very careful about that. For a total of 6 electrons. So boron onto each of the hydrogens. That uses up 4 of our electrons. We have 2 left. Hydrogen is another exception, only ever takes 2. It will never take more. So the 2 electrons left go on boron. Boron is the strange exception there. It's happy with only 6, so now we're definitely done. That gives us 1, 2, 3 electron domains, 1 non-bonding pair. So that means that it has a bent molecular geometry, which means that our symmetry is broken. Both hydrogens are on one side of the molecule. So it is polar, our first polar molecule of the evening. Nitrogen triiodide. Nitrogen gives us 5 electrons. Iodine gives us 7. Oops. A total of 26 electrons. So nitrogen, iodine, iodine, iodine. That uses up 6. Leaving us with 20. 2, 4, 6, 8, 10, 12, 14, 16, 18. We have 2 electrons left over. They will go on nitrogen. Meaning we have 4 electron domains. 1, 2, 3, 4. And 1 non-bonding pair. So it is a tetrahedral electron domain geometry and a trigonal pyramidal molecular geometry. So it looks more like this. All of the iodine are on one side, and it is another polar molecule. So now we have chlorine tetrafluoride 1 plus. That's 7 electrons from chlorine, 7 electrons from each of the 4 fluorines. We subtract our charge, meaning we have 34 electrons. So that gives us chlorine, fluorine, 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 fluorine. That uses up 8 of our electrons, leaving us with 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And we put the remaining on chlorine as a non-bonding pair. And really quick, we can look at our formal charges. Each fluorine has 2, 4, 6, 7. So it's 7 minus 7 for fluorine gives us 0. 0 formal charge on each of the fluorines. Whereas chlorine has 2, 3, 4, 5, 6. So that's 7 minus 6 is 1 for chlorine, which is good because the molecule has a positive charge. So we have 5 electron domains. We have 1 non-bonding pair, which means we are looking at a trigonal bipyramidal electron domain geometry and a seesaw or bisphenoidal molecular geometry. Okay, so this is another polar molecule. Now, sulfur pentafluoride 1 minus. 6 from sulfur, 7 from fluorine minus our charge gives us a total of 42 electrons. So sulfur, 1, 2, 3, 4, 5. That uses up 10 electrons, leaving us with 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Meaning we have 2 left over that go on sulfur. So we have 6 electron domains, 1 non-bonding pair. So that's an octahedral electron domain geometry, and a square pyramidal molecular geometry. So, once again, the symmetry is broken, and we have a polar molecule. And now let's do something super weird. Xenon pentafluoride 1 plus. Xenon gives us 8 electrons. Fluorines give us 7, 5 fluorines. When we subtract our charge, gives us 42 electrons. So xenon, fluorines, gives us 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Leaves us with 2, which goes on the xenon. It's a non-bonding pair. Has a positive charge. If you check, you'll find that the formal charge on xenon is positive 1. It's 0 on all of our fluorines. Giving us 6 electron domains, 1 non-bonding pair, an octahedral electron domain geometry, and another square pyramid for molecular geometry. For another broken symmetry and a polar molecule. All right. Apologize again for the snafu today. I will try and figure out what the hell happened. I hope you all have a nice weekend, and I'll see you Monday for the test.